Okay, here are some more examples on the limit comparison tests. So number 5. So in order to figure out what I want to compare it to, I'm going to go ahead and pick the biggest power. If you have a fraction, the biggest power on the top, biggest power on the bottom. That determines how the graph is going to behave in the long run. So the series that I'm going to compare it to is going to be really 1 over n, because n over n squared reduces to, or simplifies to 1 over n. And I know this is a p series that diverges. So now I will go ahead and do the limit comparison test, which says take the limit of the general term, the original, divided by the what you're comparing to, which is the same as multiplying by the reciprocal. And degree on the top is n squared, degree on the bottom is n squared, so the ratio of the lead coefficients gives me 1, which is a positive real number. So that means that this will also diverge by LCT. They do the same thing. Okay, looking at number 6. The only thing on top is 1. The biggest determinant of what's happening to that function on the bottom, or that series on the bottom, is 2 to the n. So I am going to be comparing it to 1 over 2 to the n. This is a geometric series. R is 1/2, so I can say it converges. So I'm going to do a limit comparison test. So I'm going to take the limit of the original divided by what you're comparing it to, or multiply by the reciprocal. And you can do L'Hopital rules multiple times. When you do L'Hopital's rule, the derivative of -1 will drop out. So this limit is really 1. So it's a positive real number, so I can say the original series also converges by DCT. Basically it does the same thing to what you're comparing it to. Okay, number 7. Okay, again, if I take the highest power on the top and bottom, you can keep the 3 over 4, it's up to you. I'm just going to go ahead and compare it to 1 over n squared, which is a p series that converges. Again, limit comparison test, the original divided by what you're comparing it, or the reciprocal. Again, notice you end up with powers always on the top. 3n to the 4th, 4n to the 4th. Ratio of the lead coefficients, this limit is 3/4. You may get a different limit if you kept the 3/4 in this series that you're comparing to, but the conclusion is the same. You still get a positive real number, so I can say that the original series also converges by LCT. Okay, this last one, number 8, is a little bit odd. It's not your typical type problem, but I do see this 1 over n, which we have worked with before. So I'm going to compare it to this. That's the only thing in here that looks somewhat familiar. So I'm going to compare it to a p series, 1 over n, which diverges. Same thing. Limit, sine of 1 over n, divided by 1 over n. And I'm going to keep it like this instead of multiplying by the reciprocal, because notice what happens. When I plug in infinity, I get 0 over 0, which allows me to use L'Hopital's rule, which gives me the derivative of the top divided by the derivative of the bottom. Notice the negative 1 over n squared drops out. I plug in infinity for n, which gives me 1. So I can say the original series diverges as well by LCT. Again, the idea is you can compare to something that it behaved very similarly to. So the only thing that's happening here is the function is 1 over n. You're just taking the sine of it, so you can compare it to the original function 1 over n.